Back when we first started talking about the derivative, I established these three relationships here. I said these three terms, the derivative, the slope of the tangent line, and the instantaneous rate of change are just different ways of saying the same thing. Well, now I want to talk more about what this instantaneous rate of change definition, it's a way of looking at the derivative, what it means in practice by looking at a number of examples. We're going to draw from three different fields to do this. One of them is going to be physics and mechanics. We're also going to talk about some finance examples, and then an example from economics. Right, so we'll start with the physics side. Right, suppose a body's position at a certain time is given by this function s of t. Right, then what is the derivative here? Well, remember the derivative is the rate of change, and the rate of change of distance with respect to time is, now if we're talking deltas, all right, this is the average velocity, and if I take the limit as delta t goes to 0 of the average velocity, we get the instantaneous velocity. Okay, now we can take this a step further, right? Suppose we go to the next step. What is the rate of change of velocity? All right, well, let's take a look at that. I'm going to do the change in velocity divided by the change in time. This is the average acceleration. Again, I'm using the physics definitions here. So if we take the limit, again, as delta t approaches 0 of delta v divided by delta t, we get the instantaneous acceleration. All right, so now let's take this back to the beginning. So if we start with s prime of t is the velocity. And now we haven't talked much about higher order derivatives, right? Beyond some of the curve sketching examples. Well, let's do this again. Now let's take the derivative of both sides of this equation. The second derivative, s double prime of t, is equal to v prime of t. And we saw up here, right, the limit as delta t approaches 0 of delta v over delta t. This is the derivative of v, and that equals the acceleration. All right, so let's see how we can use this. All right, and just kind of a very basic example to start with. Suppose the position is given by this function, s of t equals t squared plus 2, and I want a formula for its instantaneous velocity. What we saw on the last slide, that's just the derivative. So I'm going to differentiate both sides. S prime of t is equal to 2t, and that is the velocity. Now the question didn't ask for it, but we can take this one more step. Let's say I differentiate again. Right? If I take the second derivative of the position, this is the first derivative of the velocity function, the derivative of 2t, that's just 2, and that would be my acceleration. That's what this is saying now, right? The acceleration of this object is going to be constant. Okay, so now we have a very practical example. I didn't just pick the numbers in here at random. If you've taken a physics class, this is the actual equation that you could use to describe the distance fallen by a falling object. Right? And these numbers, each number actually represents something. This 2 here is the initial position. It's the initial height of the object above the ground, or whatever height you're taking to be 0. This 25, this is the initial velocity. That's how high, That's how hard the object was thrown. For example, we're talking about a projectile. And you'll see that this number here, and I'm going to kind of put this in parentheses, this number comes from the acceleration. It isn't the acceleration itself, and you'll see why in a minute when we start differentiating this. All right, so let's do that, right? I want to go all the way to the acceleration here. So I'm going to just write my function again. S of t equals negative 4.9 t squared plus 25t plus 2. Now let's take the first step. V of t is s prime of t, which is, I'll just use the power rule. Bring the 2 down. Negative 4.9 times 2 is negative 9.8 t. The derivative of 25t is 25. And the derivative of that constant, I'm not even going to write it, the derivative of the constant is 0. And now you can see, well, you can see for yourself that 25 was indeed the initial velocity. If I evaluate this at time 0, v of 0 is negative 9.8 times 0 plus 25. And that is 25, right? So you can kind of confirm what I said about that value. All right, now we want the acceleration. So let's take this one step further. V prime of, A of t is equal to V prime of t, which is the second derivative of the distance function. And if we differentiate this thing, the derivative of negative 9.8t is negative 9.8. And the derivative of 25, again, derivative of a constant, is 0. So here you can see, right, the acceleration is constant. You see, going back to my comments up here, the negative 4.9 wasn't the acceleration, but you can kind of get to the acceleration from there. And again, if you've taken a physics class, you know this is the rate. Excuse me, pen's getting a little weird. This is the rate of acceleration due to gravity on the Earth. Okay, so now I've got a similar question here, but we're going to take it a little further and see if we can't answer some questions about this, about the motion of this object. So I'm starting with a height function. S of t is 14t minus 0.8 t squared. And I know I'm being asked about velocities and accelerations and so forth. So let's go ahead and find those functions. V of t is the first derivative, so that's going to be 14 minus 1.6 t. And then the acceleration will be negative 1.6. Okay, so we have this rock, and I know, let's see what we're told. It's being thrown vertically, so this is kind of it's thrown up in the air. And I need to find the rock's velocity and acceleration at time t. Okay, good. That's what I did right here. Now, how long does it take the rock to reach its highest point? All right, well, you know what things do when they're thrown up in the air, right? It's going to start here on the ground, and it's going to go up in the air, and eventually it's going to come back down and hit the ground again. And I want to know, right, how long this is distance, or excuse me, this is time on the x-axis and distance here on the y-axis, and I want to know how long does it take to get to that point. What is this time value? Well, I'm going to apply a little physics here. Okay, the object, when you've thrown it up in the air, it has this initial velocity, right? Its initial velocity is 14, and we're doing this in meters per second, right? As it goes up in the air, gravity is pulling it back. Gravity is slowing it down. So as it gets higher, it gets slower until eventually it stops and gravity wins and the object starts getting pulled back down. So at this point here, at this apex, this vertex of our parabola, at this point, the velocity is 0. So to answer this question, how long does it take to get there? I'm going to take the velocity formula, v of t equals 14 minus 1.6 t, and I'm going to set this equal to 0. Right? And then I'm just going to solve this. I'm going to move the 14 over. Negative 1.6 t equals negative 14. Divide both sides by negative 1.6. T is equal to negative 14 divided by negative 1.6. And I get t equals 8.75. Remember, when you're doing practical problems, we're always going to add the units here for a final answer. So it's going to be 8.75 seconds. Now the second part of the question, the last part, how high does the rock go? Well, I know how long it takes to get to this vertex, and I have a function here, our original function, that tells me the height after a certain time. So what I'm going to do is I'm going to take 8.75 and use my height function to figure out the height at that time. So it'll be 14.8.75 minus 0.8 times 8.75 squared. And my calculator tells me this is 61.25. 61.25, and we're measuring in meters. I'm getting those units, by the way, I'm getting those units from the unit we were given for the velocity. So now we're going to talk about a finance example. And in the finance world, they have this concept, it's called marginality. And they apply it to just about everything. You talk about marginal cost, marginal revenue, marginal profit, marginal utility. And what it means is the cost of producing one more item. Right? So let's or the revenue from one more item, the profit from one more item, whatever measurement it is you're talking about. So I have here just a very, very basic function for us to work with for an example. This is f of x. Excuse me, got all messy. This is f of x equals x squared. And just to make this concrete, let's say this is our cost function. Okay, so I can see here from my graph, or because I know the formula, the cost of producing one unit is, and again, let's keep it simple. Let's say that this is dollars. Right, so the cost of producing one unit is $1. And I want to know, what is the marginal cost at this point? Right, well, the marginal cost is the cost of producing one more item. Right, so let's see, the cost of producing that second item is going to be 4. So the marginal cost is the difference. It's the difference between the cost of producing one item and two items. So here it would be 3. And let's just do one more just kind of to get the concept. Let's say we've produced 2 items and we get an order in. I need to produce a third item. I want to know, what's the marginal cost? How much more is it going to cost me to make this third item? Well, the third item, that cost is 9 units. So the marginal cost here is the difference between 9 and 4, which is 5. Okay, so I want a formula, right? I want to come up with a way to tell people, what is the marginal cost at various points in the production process. So let me clean up here. And let's see how we can do this. Okay, so let's take a look, right? Let me, because you want to make this a calculus thing, right? So let's say we're here at 1, and I want to know the amount that the y changes going from 1 to 2. Okay, so that's going to be this distance here. Now, here's what I'm going to do. You want this to be a calculus thing, right? I'm going to draw the tangent line at this point. All right, and here's what I want you to notice, right? I want you to notice this distance here, this delta y, is really close to this distance here. So what we're going to do is we're going to use this delta y. We're going to use this amount that the tangent line changed as an approximation of the marginal cost. And unless your function is weird, unless it's changing really, really quickly for some reason, this is actually going to be a pretty good approximation. So how can I do this? Well, look, what is the slope of this tangent line? Well, this slope of this tangent line is f prime of x. But remember what I'm looking for. I'm looking for this delta y here, right? Okay, well, if this distance here is delta x, then f prime of x, the slope of the tangent line, is equal to delta y divided by delta x. But remember, we're talking about the marginal cost here. That delta x is always going to be one item further over, right? The next item. So delta x, when referring to marginal cost, is always going to be 1, which means delta y, which is what I'm looking for, which is my approximate marginal cost, is going to be the derivative at that point. Right? So what I want you to take away from all of this, right? Anytime you hear marginal cost, right, I want you to think, okay, I'm looking for the derivative of the function, because that's going to give me a really good approximation. Okay, so I've got an example here, and we are talking about costs, right? The cost function is given by this formula, right? And I want to know, what is the marginal cost of the fifth item? Well, I know that, let me just write it here. C of x is x squared plus x plus 1,000. So C prime of x is 2x plus 1. And I know from our previous conversation, the marginal cost of producing the fifth item is C prime of 5, which is 2 times 5 plus 1, and that's 11. Right, and we're talking about cost, right? So my units here would be dollars. Okay, so we've got multiple functions this time. So suppose the cost of producing X units is this function, and the revenue is this function. So I want to do three things. I want to find the marginal cost. Let me write them here. Marginal cost. I want to find the marginal revenue. And I want to find the marginal profit. Okay, well, I have functions for the cost and revenue, so that's just a question of finding their derivatives. The marginal cost is the derivative of the cost function. That's 2x plus 1. The marginal revenue is the derivative of the revenue function, which is 125, and that kind of makes sense, right? If the price is constant, then the marginal revenue is going to be constant. And finally, the profit. Okay, here we're going to have to work a little bit. How do you determine the profit? Well, the profit is your revenue minus your costs. Okay, now you could put 125x in here for the revenue and x squared plus okay, right? And find an actual function for the profit, but I wasn't asked that. Look, let's apply one of our derivative rules. Let's just differentiate both sides of this thing. If I do that, p prime of x is r prime of x minus c prime of x. And I already know what those two derivatives are. R prime is 125, and C prime is 2x plus 1. Be careful, you notice the parentheses I added there, right? So I'm subtracting the whole thing. So this is 125 minus 2x minus 1, which is 124 minus 2x. There's my marginal profit. Okay, so that's our finance example, right? So now I want to talk about this thing from economics. It's called the elasticity of demand. And what this is elasticity refers to how sensitive the demand is to changes in the price. So let me give you a couple of examples. Cruise ships, cruise lines. They are a luxury item. They are very sensitive to changes in the price because first, people don't have to buy one. They can choose to just put it off their vacation and not buy it at all. And second, there are lots of alternative products. There are plenty of other vacation options if the cruise price gets too expensive for you, right? On the other kind of end of the elasticity scale would be something like gasoline. It's not perfectly elastic or inelastic, but you have to drive to work. You have to drive to school. Trucking companies, they have to fill up their tank and deliver goods to wherever they've been hired to deliver them. So the demand for gas is relatively resistant to changes in the price. Now, obviously, there are limits, right? People can change their driving habits, right? There are things that people can do to minimize their usage, but it's really hard to stop buying altogether and go to buy something else. All right, so how do we measure this thing? Well, this is based on comparing percentages. Right, I'm going to take the ratio of the change in demand, the percent change. That's this. So it's going to be delta Q divided by Q. And I'm going to divide that by the percent change in the price. That's this. Delta P divided by P. Okay, now, suppose that Q is equal to F of P. In other words, the demand is a function of the price, right? Well, in that case, delta Q is equal to, that's the change, right? The change in the demand is equal to F of P plus delta P. That's the new demand after the price increase, minus F of P. That's the original price. All right, so let's see. I'm going to put that into our formula, but I'm going to fix this fraction up a little. Remember, how do you divide two fractions? You keep the first one the same, so it's going to be delta Q over Q. You change the division to multiplication, and you flip the second one over. So this is P over delta P. Now, again, I'm going to rearrange this a little more. I'm going to put the P and Q together, so that's P over Q. And I'm going to put the deltas together. So that's delta Q over delta P. All right, now let's make my substitution. I'm going to replace that. I'm going to leave the P over Q alone, P over Q. I'm going to replace delta Q with this. So that's F of P plus delta P minus F of P over delta P. Okay, hopefully that second fraction there, hopefully that looks familiar, right? If you replace that delta P with H, because we usually use an H, if you put an H in there instead, that looks an awful lot like that difference quotient that we used all the time back when we were first looking at the derivative. All right, so here's what I'm going to do. I'm going to take the limit as delta P approaches 0 of the whole thing, P over Q times f of p plus delta p minus f of p over delta p. Now, the p and the q, they don't this first fraction, they don't depend on delta p at all. So I'm just going to bring those out in front. This is p over q times the limit. Delta p approaches 0. Fp plus delta p minus f of p over delta p. Right? And this is what I needed, right? This is where I was trying to go with this. That limit is f prime of p. So this is p over q times f prime of p. But back up here, my definition, right? F is just the same as q. That's my demand function. So this is p over, whoops, clean that up. This is, let's try that again, p over q times q prime. And let's make it clear, q prime of p, that is a function of the price. Okay, this is what we want for our elasticity, although the economics guy, they do make one little switch. The way elasticity is defined, elasticity is negative p over q times q prime of p. They throw that negative sign out in front. And kind of the reasoning is, look, what does q prime look like? Q prime is the demand, and we know just from your basic economics class, as the price goes up, the demand goes down. Right? So as the price goes this way, the demand goes this way. That means Q prime is always going to be a negative number. This is a decreasing function. And they kind of like for these elasticity numbers to be positive numbers. Just positive numbers are often just easier to work with. You don't have to worry about an extra negative sign floating around your calculations and whatnot. So that's why that negative number, that minus sign kind of gets thrown in front. Just make sure we're always going to be looking at positive quantities. So at the top here, I've summarized the conclusion of our calculations. Elasticity is equal to these two formulas, and all that's different here is the way I wrote the derivative. Here I use the dp over the dq over dp notation. Here I use q prime. Whichever one is clearer to you. I usually use the q prime, but it's the same thing either way. And then down here I've got kind of what these things mean. If the elasticity is less than 1, then that means that revenue increases as price increases. In other words, the product is a necessity. So a change in price has relatively little impact on the demand. Right now, the other way around here, the demand is elastic if E is equal to 1, and that means that revenue decreases as price increases. In other words, the revenue will change. Right? If you change your price, you can expect there to be a change in demand for the worse. Right? Revenue is going to decrease, which means people are not buying. This is the case where the product is not a necessity. So let's see how these work. Right, let's do an example. Right, the demand for crude oil in the United States is given by this function here. Right? And I want to know what the elasticity is. What's the elasticity of demand when the price specifically is $100 per barrel? All right, well, let's use our formula. Right, elasticity is negative P over Q times Q prime of P. What I want to emphasize to you here is P is the independent variable. P is like the X in this situation. All right, so I'm going to leave that negative P just the way it is. And down here, I'm going to put my formula for Q. There's some weird numbers here. 2431129 P to the negative 0.06. Okay. Now I need the derivative. Well, I know the numbers are big and kind of weird looking, but look. That's just a polynomial. Well, that's not a polynomial because the exponent is negative. But this is p to a power, p to a number. So the power rule applies here, right? What am I going to do? I'm going to leave the constant out in front the same, 2431129. I'm going to multiply by the exponent, negative 0.06, and I'm going to reduce the exponent by 1. Now you see why I was looking ahead. You see why I didn't try to multiply that out? These big numbers here, they're going to cancel. Right? They're going to cancel. Then what happens? Let's see. The two negative signs, they cancel each other. So I'm left with 0.06 times p to the negative 1.06 divided by p to the negative 0.06. Now, you know how we do exponents, right? You add them all up. Well, you add in the numerator when you're multiplying. So this is a 1. So the final exponent will be 1 plus negative 1.06 minus the exponent that's in the denominator. And if you work these out, this comes out to 0. Right? So this is 0.06 p to the 0 power, which is 0.06. And that's it. That's my elasticity. Right? It turned out to be a constant. And what is the elasticity when p is 100? Well, it's 0.06, right? Because it's a constant. All right, so what does that mean? Well, look, this is less than 1, right? That means this is inelastic. In other words, the product is resistant, the demand is resistant to changes in the price, right? And that's kind of what we expect from oil. Oil is used to make gas and petroleum products and so forth. It's not something that you can easily do without. It's not something for which there are a lot of substitutes, right? So that's good. That's the kind of number that we expected to see for this particular type of product. So where are we going next? Well, in first semester calculus, we're really usually only concerned with one variable at a time. For example, when we're looking at the physics examples, the independent variable was time. Right? When we're talking about our elasticity examples, the independent variable was the price. Well, what we're going to do in the next section, we're going to take kind of a brief glimpse into what happens when we have more than one variable. Right? So we're going to look at things like the formula for the area of a circle. Area equals pi r squared. And let's say we have a situation where the radius is changing with respect to time. Well, if the radius is a function of time, then the area is also changing with respect to time. So in theory, I can differentiate both sides of this equation with respect to t, right? And when we do that, we get a class of problem that's called a related rate problem. Right? And before we do that, just kind of looking ahead, this would be a good time to go back and do a quick review of the chain rule. Right? Because the chain rule, again, just looking ahead, the chain rule is going to be a really important tool when we get to this next section.